Hello, today I'm going to be going over my final project for AIPI 520, which is a end-to-end machine learning pipeline for the human activity recognition dataset, also called the HARTH dataset. So we're going to be comparing two models. The first will be a random forest model, and the second is going to be an MLP neural network model, also called a multi-layer perceptron model. So in this data set, we have 22 subjects wearing sensors at both the back and the thigh. These are accelerometer sensors, and at a 100 hertz sample rate. There's 12 total activities such as walking, sitting, cycling, etc. And there are 6.4 million raw samples. So the first step in our end-to-end machine learning pipeline is the data cleaning process. So here we see on the left that we have 12 activity classes. We have walking, running, shuffling, stairs up, stairs down, standing, sitting, lying, cycling, sitting, cycling, standing, cycling inactive, and car. So the first thing that we do is we load and tag all the subjects. So there's 22 total CSV files, one for each subject. We read each file individually, assign them a subject ID for each data frame, sort it by timestamp for each subject, and then concatenate all of them into one data frame. So that way the subjects stay in order, but the timestamps are sequential. So next thing we do is that we encode the labels so that we map the activity codes to consecutive integers, whereas in the raw data set they were a bit arbitrary at 1, 3, 4. It even got up to something a little random like 140. So this is the first step in our machine learning pipeline. The next step in our pipeline is feature engineering. So here we did a sliding window strategy since we were dealing with time series data. So we used a 2-second window because there was one sample every 0.01 seconds because it was 100 hertz. And we used a 100 step size. So there's a 50% overlap between each window, which gave us 58,523 windows total. So this allowed the model to work with much more meaningful data since it wasn't just insanely granular data points from the time series. So for each window, we extracted some features such as the mean, standard deviation, min, max, energy, and range. And then we did that through all 6 sensors. So the final feature vector is 36 total. So when we look at the shape of this feature vector, 58,523 by 36. The evaluation metric I decided to use is macro F1. And the reason I decided to use this is because I actually found that there was a huge class imbalance between all of the different activities. So for example, looking at subject 6, the activity of sitting comprised 62% of all of their samples. So if you were to train a model that just predicts sit all the time, it would be 62% accurate. So it's not a very strong metric to choose. So we choose F1 because it weighs each class equally. So some of the more rare activities like stair climbing, which only has 10 windows compared to sitting, which has over 2,000, it can get weighed equally, and the model can be more accurately evaluated. So another thing that we do is something called leave one subject out cross validation. So this is a good strategy here because it's realistic of real world deployment. So in the real world, you train on known users and then predict on new ones. So what we do here is we go through all 22 users, 22 subjects, leave one of them out, and then evaluate or test on that one subject. So we train on 21 out of 22, test on one, do that 22 times by leaving each group out once, and then we average the scores at the very end. This is a very strong way to do this because you don't have subject leakage. You have 22 total folds, so each subject gets a turn at the test set, and then there's a consistent split. So yeah. So the first model trained is a non-deep learning model. It's a random forest model, and this one had a very high accuracy at 94.6%, but a somewhat average macro F1 score. And this is to be predicted because, again, looking at those class imbalances, some of the activities like stair climbing was very, very rare and minimal, and so it probably had very poor predictions on those. We'll look at the classification reports later. But the reason we choose random forest here is because it naturally handles these tabular features very well. So when we think about the windowing and feature extraction that we did on the time series data, random forest does very well on that. It has non-linear splits, so it captures these complex interactions between all the different axes that were used during the data collection process. It ranks feature importance, and then it also has a parameter where it balances out class weights, so it's able to optimize some of the more rare classes and balance those out with some of the more major classes. The next model we train is an MLP neural network model. So that's a multi-layer perceptron model. And as we can see, the macro F1 in accuracy is slightly worse than the random forest model. So macro F1 sits at around 0.64 and the accuracy is 93.1%. So while the accuracy is still high, the macro F1 is pretty poor here. And the main reason why is because the neural network model just doesn't quite handle these class imbalances as well as the random forest model. The random forest model has a very strong way of separating out these linear differences using the features, whereas an MLP neural network model requires much more training and data to get to a place where it can accurately determine between various classes. So looking at the per class performance here between random forest and MLP, we actually see that they are pretty similar in how accurate they are on each class. So classes like walking, running, standing, sitting, lying, and cycling, sitting had pretty high accuracies. And I think the reason why is because these sensors and accelerometers are able to capture this range of motion when the subjects were performing these activities, and it's very accurate and telling of what's actually happening. Whereas some other activities like stairs up or cycling, sitting, inactive can be a little bit harder to determine because the range of motion across the accelerometers isn't quite as telling of the story of what's actually happening. And so the models have more trouble determining what is happening. So the summary here is we trained an end-to-end pipeline on the human activity recognition dataset, 22 subjects, 12 activities using a sliding window and leave one group out cross-validation. We went through feature engineering where we were able to capture 36 features per window, mean, standard deviation, min, max, energy, and range across 6 channel sensors. We trained a random forest model that achieved a 0.708 F1 score. Not the best, but looking at the class imbalance, it makes sense, and it was strong at some of the more telling classes such as walking and running. Also an MLP neural network, which was at a 0.640 F1 score. And some of the key lesson that we can take away from this is that pipeline correctness matters the most. So when I was running through this project, my F1 score at the very beginning was at 0.34, and that's because I wasn't doing the windowing correctly, and there was actually cross-subject contamination. So between windows, there were different subjects, and so it was harder to actually capture the movement that was going on. And what I did is I changed that to a 0.80% majority class label on the window, and then if it was higher, or if it was lower than 0.80 on a window, then we would toss that window. So that raised our F1 score from 0.34 to 0.71.